Hello, I'm going to be presenting a C3D tutorial on how to set up a radiation view factor calculation, predicting the heat up of an aircraft on top of a ground surface which consists of concrete. What you're looking at here is the final result after about 20 seconds of heating up. It went up about, I'd say about 30 degrees on the ground and a little less so on the aircraft. The aircraft in this case is bare aluminum, and the ground surface is concrete. Now, to do this radiation simulation, I'm going to be using the C3D code. C3D was originally developed at the national laboratories, primarily at Sandia, and it should not be confused with another code also called C3D, which is actually Civil 3D by Autodesk. They are not the same code. The C3D code is actually a fire code uh, developed primarily for combustion applications, but it will also do just plain old radiation, which is what I'm going to demonstrate here. So the first thing we want to do is create a new project, and it'll be heat transfer and fluid flow. There won't be any fluid flow in this, but uh, you can just basically just turn that off. So we'll go into modify, and the first thing we want to do is get some properties of materials. The default properties, when you bring up the default application here, we have insulator, which has zero conductivity, steel, and aluminum. The aircraft that I showed earlier is going to be made of aluminum, but we need to have a couple of other properties. So I'll right click. Whoops, I don't want to do that. I want to browse the database. So we want to add concrete for the ground surface. So double click on that. And graphite for the hot surface. Double click on that. And we now need to edit the radiation properties of these materials. Let's see, the surface emissivity of aluminum of 0.2 is good. Concrete, surface emissivity is around 0.8. Okay, and we're going to make the surface emissivity of the graphite equal to, let's say, 1. But we also want it to be real hot. We're going to put in 2500. And we don't want it to cool off at all, so let's make that E3. If we increase the specific heat over this short duration calculation, it won't cool down at all. Okay, so now we have the material properties that we go on. Click on OK. The next thing we want to do is to go into geometry and set all of that up. So we go into geometry, and we already have a default computational domain, but it's not of the proper size. The airplane STL file that I have, I need to make it fit. So for the X dimensions, I'm going to use negative 18 meters to plus 15 meters. The Y dimension is going to go from minus 18 to 18. I'm picking these dimensions so that the airplane just fits in this thing. And for the Z dimensions, we're going to go from a minus 0.1 so that we can include the ground surface. It'll go from minus 0.1 to 0 and up to 20 meters high. The hot ball is going to be at an elevation of 20 meters. And let's see, the computational domain, we'll just fill it with fluid, or basically air, at 300 Kelvin. So the next thing we want to do is to add a ground surface. So it'll be a rectangular region. We'll call it ground. And it's going to be going from minus 18 to, it'll be basically the same X and Y as the domain, minus 18 to 18, and it's going to go from minus 0.1 to just the top of the ground surface, 0.1. And we're going to make this material, well, we'll just use concrete. Okay, so we're not going to map that to a subgrid. We will do that with the airplane though. Okay, and the next thing we want to do is add the airplane. So we want to bring in a STL graphics file. We'll call this, it's got to be the name of the STL file, airplane.stl, and I've got to get some parameters here. I'm going to pause this thing for a moment. Okay, I'm back with you. I had to go get the parameters to figure out how to fit the STL object in the computational domain. So I'm not going to shift it in X or Y, but I am going to shift it up 2 meters in the Z direction. And the STL file came in, I believe, centimeters. So to get it to meters, I need to give it a scale factor of 0.01. And it's going to be made of insulator. Why is this uppercase? Windows may not care, but Linux would, STL, because it's case sensitive. So just to be safe, I'm going to put in the actual file name, insulator. Now what we're going to do is map this to a subgrid made of aluminum. Okay, so we're done here. We have everything we need. Click on OK. I'm going to save the data now. Let's see. I already have a directory set up. I just got to find it. Airplane, here it is. View factor. And we're going to call it C3D. Okay, now the next thing we need to do is to, well, let me show you that the boundaries are all set up to be insulating, nothing going on, and we're going to leave those as they are because this is a non-fluid flow problem. It's radiation heat transfer only. Well, let's go ahead and mesh it. We have to get the correct dimensions, so I'm going to do a delete scan and mesh. I wish it wouldn't make that noise, but we're going to put in 100 by 100 by 100 grid in the X, Y, and Z. Okay, and the Z direction, remember we have a ground surface, so we want to take care of that, and we'll put in 101 so that we have one cell for the ground and 100 going up to the top of the mesh at 20 meters. Okay, so we're done meshing it. Now what we want to do is to map the airplane skin to a subgrid. So I'll call this skin. Well, let's call it airplane. And we'll call this part name skin. You could add other parts, so there could be a whole bunch of things here if you wanted. I'm guessing the thickness is going to be 5 millimeters, well, 0.005, and we'll put in just one. The conduct, it's not going to have a thermal gradient in it because it's so thin. It'll all heat up uniformly. We have to give it some fluid, even though we won't use it. It has to be in there, and it's going to be aluminum. And we're going to do geometric coupling. You can't use coupling material because of the way things are set up in memory. It has to be set up to the file name. And we're going to search the entire domain. For boundary conditions, we'll just give it insulating. That's okay. That's the default, and that's okay. So it's all insulating. Now we have everything we need. Okay, and we'll save that again in the same place. Output numerical. I think we want to add some VTK files. We're going to get them anyway, but let's make sure that that would be too many. We want to have one every second. Okay. Now let's go into time step. Oh, we want to make sure that radiation heat transfer is turned on. So we go into numerical parameters. Okay, so we want to click this surface to surface view factor because that's all that's going on in this problem. Save. I think this is going to run for 0 time steps. Let's put in 0. And the reason I want to do that is to show you what happens if you map all the surfaces in the problem to each other. Save. Okay. Now we'll go ahead and run it. So before we run it, there was actually a couple of changes I have to make. One is I forgot to put in the sphere at the top, the hot sphere. And the other one is we really need to map the ground surface to a subgrid so that we can actually see its temperature and track the temperature gradient going into the ground. So we'll go back to geometry, and what we're going to do is add a sphere. Right click, it'll be a spherical region. We'll call it hot sphere. And the position will be, X will be 6, Y will be 0, and let's put it all the way at the top, 20, and a radius of 3 meters. Initial fluid 300 is okay, and we want it to be graphite, which is the hot solid. Okay, that does that. All right, so we're done here in the geometry. Oh, there is one other thing. Let me go back to geometry. We want the ground to be insulator, okay. I had changed that before, not in this video, but a couple of minutes ago, so it is the material we want it to be right now. We go back to subgrids, and we want to add a subgrid, and that'll be the ground, G-R-O-U-N-D. I'll just call the part G. Give it a length of 0.2, and let's say 5 cells if we wanted to track the temperature gradient. Initial fluid of 300, and it'll be concrete. Auto coupling, and we're going to look for insulator to couple this surface to it. Search the entire domain and double click on boundary conditions. We can just take the default, which is insulating, and so the only thing that's going to happen is it's going to absorb radiation. All right, call this ground. GR. Okay, I think that pretty much covers it. Save data. Okay, now we have everything we need. Before we actually click on run, I wanted to show you what's involved. We have a ground surface 100 by 100. So there's 10,000 polygons in this. And if we zoom in on the aircrane, you can see that there's lots of surfaces in there, including such things as the details of the engines. There's a lot of polygons in here, so it has to look at every polygon and come up with a view factor. And so, as well as we also have let me bring it down, we have the hot sphere up on top. So there's a lot of polygons involved in this particular simulation. And that's what we're going to be calculating, view factors between every polygon here and every other polygon on this in this entire model. Okay, so the next thing we want to do is to go in and run the code. And I'm going to run it for 0 time steps. The reason for doing that is I want to show you how many view factors get created with all of these surfaces that are involved. So, okay, the code is continued and it's now calculating the surface-to-surface view factors. Now, it's going to be a lot of them because we have a mesh of 100 by 100 by 100, which is a million cells. And then there are something like 70,000 surfaces in the airplane. I've forgotten the exact number. Actually, I can scroll up and take a look here. Yeah, it was 160,000 surfaces in the airplane, and it's looking at all the surfaces on the ground surface as well. So there's going to be a lot of surfaces involved. I'm going to put this on pause while it calculates all these view factors, and I'll come back as soon as it's done. Okay, so it's finished calculating all the view factors, and if you look at this number, it's enormous. That's 1.3 billion. That's billion with a B view factors. A case like that will not run on this computer. That's way too many view factors. So I'm going to stop this particular calculation and show you how you can run it. So the way you fix this problem is well, let me bring up an image to show you what I mean. So here's an image of the model that we have. What we're going to do to make the problem a runnable problem is get rid of all these view factors where tiny irrelevant surfaces can see each other. Like, let's take a look at this engine, a close-up. You can see these tiny surfaces. It's calculating a view factor from there to say that, all these other elements. It's not something that is relevant to, as far as the heat transfer problem goes. The only heat transfer that's going to occur in this problem is from this hot sphere down to the airplane and the ground surface. So what we can do is we can restrict the view factors to be only from the hot sphere down to these other elements. And I'll show you how to do that. So what we do is we go back into the modify, go back to numerical problems, the energy equation, and what we want to do is put in a view box. If it has zeros, that means it goes the entire dimension from x min to x max, y min, y max, so on. But what we want to do is restrict the z min to go from just below the sphere to the top of the domain, from 15 to 20. Okay, and what that'll do is it will restrict the view factors to be only from those locations. Let me save that, and we'll go back and run it again. All right, now it's calculating view factors. I'll put it on pause for a moment. Okay, so it's done calculating the view factors. As you can see, the number went way down. We're looking at 15 million as opposed to 1.3 billion. That's a huge factor of 1,000 reduction. And so now this actually is a problem that you can run on this particular machine. So I had set it up to run 0 time steps. Now I'm going to go in and let it run for 20 seconds. Close this, go back into modify, time step, max step, we'll set that at 10,000. It won't take that many, but we'll put in a stop time of 20 seconds. Let's put in a max time step of 1/4 second. You can start out with, say, 0.01 for a minimum time step. Okay, and so for equations, what we want is no flow. Well, no, constant flow. What that's going to do is it will set up the flow to be at the initial conditions, which is basically 0 everywhere. So no flow is if you have a completely solid object. We do have air in this system, so what we want is constant flow, and the flow is initially set up to be 0, so it will keep it 0 for the duration. We save that. Okay, now we'll go back and run it. Okay, the problem is now running. It's going to print out a little bit of data every 5 time steps. So you can see that it's getting there. It's printing out a VTK file every second. There's the second one. So it's running at a speed that's not bad for 15 million view factors. So I'm going to let this problem run to completion. It's probably going to take less than 5 minutes, but I'll put it on pause while it finishes. Okay, so the problem is finished running. Now all we want to do is open ParaView and have a look at the result. The temperature data, let's see, open, is stored, the pv.vtk files, that has the flow data, of which there isn't any in this problem. And the temp1ds, this has the temperature of the surfaces. So we open that, apply, and we'll go to the very last time step. Now we don't want to look at subgrids, we want to look at surface temperature. Now it does look, remember the sphere at the top was at 2500 Kelvin, so we want to restrict it to be something where we can see the ground. Let's put in 400 and see what we got. That might be a little high. Try 350. Okay, pick a different color scale. 350 is also a little low. Let's try 380. Okay, so that gives you an image of, or a view of what's going on here. We have the hot surface up here, 2500 Kelvin, shining down on this airplane. The top of it's getting hot. This is a 20-second run. It was aluminum, 5 millimeters thick, and it's heated up 80 degrees over that time scale. And you can see that there is shadowing going on. So that's included in the view factor calculation because the sphere up at top cannot see underneath the airplane. So you get the shadowing. The ground is not heating up very much. Looks like maybe 10, 20 degrees. And there's some interesting details, like you can see there's heating of the engine, but those surfaces up there cannot see the hot sphere. Some of the blades in the impeller can see it. And so, as you can see, this is for anyone that's interested, a way of calculating radiant heat transfer from one surface to another. That pretty much concludes this tutorial.